Hi everyone, we are the team 1155 presenting the problem A. The team members are Elim Graell, James Villarreal, and Jerry Wilson, coached by Professor Idulfo Arrocha, and we are representing the Technological University of Panama in Panama City. For the problem statement, a recent study demonstrated that some chocolate products may have high levels of heavy metals. Eating contaminated chocolate may lead to the bioaccumulation of materials in the people who eat chocolate treats. Assuming the results of the survey are correct, it suggests that regularly eating contaminated chocolate may lead to a gradual accumulation of heavy metals in the body over time. In this research, we are studying specifically cadmium and lead levels. The main objectives we got for this problem are to construct a model that helps to track how heavy metals levels might impact in the human body during time in different proportions of consumption. Also, with the information we gather from the first point, determine what happened to children who consume large amounts of infected sweets at certain times of the year. And finally, to compare if there is a difference between regulating the amount of intake on a holiday rather than allowing a child to binge during it.
To solve this problem, we will consider a compartmental model. It allows to describe one or more compartments where there is an inflow and outflow of a substance. It is often used to describe transport of material in biological systems, where every compartment has a number of connections leading to the box, or inflows, and a number of arrows leading from the box, or outflows. The general concepts arising from compartments can all be described by studying a single compartment. With this, we can make predictions for our model considering the individual as a single compartment, where I function of t represents the inflow function or the rate of daily metal concentration intake. O function of t represents the outflow function or the rate of elimination of the metal concentration. And C of t represents the concentration of the metal. The ordinary differential equation that describes this model is the equation number 1. The outflow function is described by the next expression, the equation number 2, and K represents the rate at which the metal concentration decreases in the body, obtaining our final expression or differential equation to describe our model, the equation number 3. As this model represents a linear ordinary differential equation of first order, we can multiply each term of the equation by the factor u, obtaining in this way the equation number 4 that allows us to solve this ordinary differential equation for any function I of t. One of our assumptions will be that k will be calculated using equation number 5 as it behaves with an exponential decay, where t half represents the half-life of lead and cadmium in months and years respectively. Based on our research, we obtained t and a half for lead, a period of 28 days, and for cadmium, 23 years, obtaining the values of k shown on the slide. Assuming a constant function of daily consumption I of t equals I, we obtain the final equation number 6. And also we will assume that z sub 0 is equal 0 and I is equal n times the concentration of the chocolates that are shown on the slide. For lead concentration for different levels of consumption of n times the concentration of the chocolate, we obtain this family of graphs. And for cadmium concentration for different levels of consumption, we obtain this family of graphs. To describe a children who might consume a large amount of candy at certain times of the year, we will make the following assumptions. The constant k is the same for children. We will only use the model for the lead as it allows to describe the same consequences at cadmium. The function I of t will behave as a piecewise function. We will consider that the epoch of holidays is between the months of November and December. And finally, we will consider that the case for a child whose birthday is in May, far from holidays, and other one whose birthday is in October, near to holidays. For the intake functions, we will consider for normal daily intake 0.25, for birthday month daily intake equal 1, and for holidays 1.25 micrograms per gram. With these assumptions, for case number 1, far from holidays, these were the intake function, and also solving the ordinary differential equation model for each interval, then we obtain the following C in function of t. The lead concentration for a child with a birthday far from holidays, we obtain this graph with the special points A, B, C, and D, where the x-axis is represented by time in months.
For case number 2, we will consider the child's birthday to be near the holidays. We will consider the following intake functions, where the first one has a lower than 1 intake concentration ratio between January and September. Then, during October, the regular amount of concentration, and then, during the holidays, a slightly larger than normal intake concentration ratio. We obtain the following solutions to our differential equations for the concentration function for the corresponding intervals, considering that the initial concentration is once again 0. From the previous solutions, we obtained the following graph for the lead concentration for a child whose birthday is near the holidays, where the y-axis represents the concentration and the x-axis represents time in months. Here, we mark the special points A, which corresponds to the beginning of the child's birthday, B, which corresponds to the end of the child's birthday and the beginning of the holidays, and C, which shows the end of the holidays period. Now, moving on to our final question, we will compare the lead concentration levels for a child who consumes their candy over a long period of time after the holidays versus consuming all of their candy during the holidays. For this, we will take into account the following assumptions. The daily intake is 0.25 micrograms per gram. The period after holidays will be assumed as beginning on May. The period of holidays will be assumed to be on December, and we will neglect any potential increase in candy consumption caused by the child's birthday. For the case where the child consumes their candy over a long period after the holidays, we will consider the following functions for the intake, where the child will consume a small amount of candy between January and April, a larger than normal amount of candy during May, and then going back to the previous candy consumption through the rest of the year. We then obtained the following solutions from our model, considering the initial concentration to be 0. Plotting the previous solutions according to their respective time intervals, we obtained this graph showing us the concentration levels on the y-axis and the time in months on the x-axis. The points A and B represent the beginning and end of the long time period respectively, and the point C simply marks the final value of the lead concentration levels by the end of the year. Finally, we will consider the case where the child binges on their candy throughout the holidays period. We will now consider this intake function divided into 2 intervals, the first one with a low intake ratio between January and November, and the second one with a high intake ratio during December. Once again, we can see the corresponding solutions using our model. Plotting the solutions, we obtain the simple graph with points A and B marking the beginning and end of the holidays period respectively. The concentration levels are in the y-axis and time in months in the x-axis.
For the conclusions, it is observed that if children keep consuming treats highly infected with both lead and cadmium, it will accumulate in their bodies over time. Also, by comparing case 1 and case 2, we determined that children whose birthday is near to holidays, they would have a higher concentration, especially in the month of December. Finally, there is no difference between lead and cadmium concentrations in the bloodstream if we allow a child to binge during a holiday than allowing them to eat after it. For the recommendations, due to the alarming levels of the two metals, we suggest to large companies better treatments to the cocoa beans, which are the ones that are mostly infected due to their way of cultivation, as a way of decreasing its presence in chocolate bars. We also would like to encourage parents to keep that great hard work of regulating and even decreasing the amount of consumption of cocoa products, as it has severe negative impacts, especially in children.
Lastly, here are the references used throughout our research. To close things off, we would like to personally thank our differential equations professor, Idulfo Arrocha, for coaching and preparing us for the development of this presentation. Thank you for listening.